Right. Good afternoon, everyone. So I'm here to talk to you about pruning and quantization. A bit about myself. I'm a senior data scientist at Eaton. Eaton is basically a manufacturing company. It produces hundreds and thousands of things. It's more than 100 years old, and it has offices all over the world, and so in Dublin. In Dublin, we have a team called Center for Intelligent Power, and that's what I'm a part of. And what we mainly do are these things. Of course, data science, some UI, UX kind of thingies, and most importantly, intelligent machines. So what the Center of Intelligent Power is trying to do, it's trying to embed intelligence in power electronics, basically, or like the electrical thingies here. For example, your MCBs, we're trying to embed intelligence into those MCBs so that advanced analytics can be done and loads can be protected and things like that. So we're trying to bring intelligence closer to these kind of systems. So the project, I joined Eaton recently, by the way. Before that, I was working for CEDA, Center for Applied Data Analytics at UCD. And there I worked on this project on Edge AI, which I will mainly talk about, and pruning and quantization are part of it. So in that project is where when we developed this whole power pipeline, where we had a problem, then we designed a neural network for it, trained it, pruned it, quantized it, wrote an embedded code for it, and then deployed it on an actual edge device. You can check this project out with this link here. You can just Google CEDA Edge AI and it will come across for sure. And I was helped by Adnan Ashraf, who was doing his research masters in UCD at the time, and supervised by Deepu and Oshin, both of them working for UCD. All right, so before jumping into the actual topic, just to get a sense of what the background is in the room. So a show of hands for people who know what deep neural networks are. It's a super question, everybody knows, okay. And how many of you have actually used Keras, PyTorch, TensorFlow to train? Okay, good. How many of you know about pruning or quantization? Okay, very few. And how have you actually used it? No, okay. You know the concept. Okay. Okay, that's an easy crowd. So you'll believe whatever I say. All right, so but we'll start from the very basics. All of you know neural networks. The basic inspiration comes from a biological neuron. You basically model it. This is the most common mathematical model for a neural network, where you have weights and you multiply those weights with your inputs and then you add them. And then there is an activation functions of sort. So this is called a multiply and accumulate operation, a MAC operation. I'll be using that throughout the presentation a lot, so get a hang of it. And somehow what you do is you put these neurons in weird configurations, and somehow you get a neural network, which is very useful for many things. And some people do understand why do they work. I personally don't. And one of the outcomes of this talk, one of the things I wanted to convey is what I learned about the basic structure of neural networks when I did this pruning and quantization exercise. So, what is the problem? The problem is, let's take VGGNet. And somehow, this is not the slide I wanted to show. There you go. All right, VGG16 is a popular neural network, came a few years back, not that big. So let's just load it from PyTorch and see what it is. Of course, VGG16 has 16 layers. Every layer has a good few parameters. And the total parameters in it are about, so it has around 138 million parameters, right? If you look at PyTorch, so the default data type in PyTorch is torch.float, which is a 32-bit representation of a number. That means each of the weight or the parameter of that neural network takes about 32 bits in your memory, right? Simple math, you multiply the number of parameters with the number of bits you take, you end up with about half a gigabyte of memory that is needed to store this neural network in your system. And this is at the crux of the problem. Because if you go to a typical embedded system, or typical edge device, I should say, not an embedded system, the memory in this is orders of magnitude smaller than what a typical neural network is. And VGC16, mind you, is like, I think, good few years in the past. Now we have neural networks touching like billions of parameters, or a couple of billions in some cases. So for the project I was doing, we used this BMD 340 board. Some of you might know it. This board is a popular board for wearable design. So it is a low energy Bluetooth module. And the processor it has is an ARM processor called XM4, if some of you are aware of it. And it has only 256 kilobyte of RAM and about a megabyte of flash memory. So the problem is, how do you embed this half a gigabyte of a mammoth into this tiny device? And this is true with many of the devices, the projector here, the microphone, like they have like extremely small little memories and even processing power. So how do you get these big neural networks from there to there? So how do you solve this problem? Any guesses? Like, okay, so one of the first things is, use a different one, a smaller neural network. Though it is not in the title of my presentation, but yes, this is the thing which is most commonly done. So I'm going to spend a few minutes on it. Also, one other thing, I'm not going to structure this talk like a typical conference presentation. It'll be more high level in the sense of what I learned from the talks. I wouldn't be presenting what the accuracy was or whatever the class imbalance, those kind of things. So briefly about the problem, we were dealing with anomaly detection in heartbeats. So you have a sample of a heartbeat and you wanted to detect whether it was anomalous or not. And we wanted to use a neural network for it. So we started with an autoencoder based anomaly detection. Some of you might know it. You feed an input to an autoencoder and what you get at the output should be the same as input. And based on that reconstruction error between input and output, you label it whether it's an anomaly or not. So we trained our autoencoder on normal heartbeats and then just let all the heartbeats go through it and decided, and if the reconstruction error is high, it's anomalous. But try to understand what an autoencoder does. What it does, it takes your input, it compresses it into a latent space and then decompresses it. So the idea is that this latent space somehow could represent all your signal, right? So we kind of made the use of this and we decided to chop the decoder off completely. So after we trained our autoencoder, we chopped off the decoder, we took this encoded layer and fed it through a classification layer, right? So you immediately reduce the size of your model by half and then you keep the same accuracy. I'll come back to this idea. This is it sounds like a fairy tale, but it has some backing to it. We'll come back to this idea towards the end of this presentation. Another thing, neural networks are these very extremely compelling things, you just feed in data and you get something out of it, out of the blue, and it's very compelling to use them. But sometimes you forget that what neural networks are trying to do, they're trying to learn those features themselves, which can help you, let's say if you're doing classification, which can help you classify things, right? But what would happen if instead of feeding it raw data, you actually feed in some features, which many of you might have done. So we tried this. In many other papers, there are things called, some of you might have heard about this, skewness and kurtosis. These are like statistics about a distribution. And the other papers also use this something called RR. So these are peaks between two heartbeats. What we did, that instead of having a big neural network, which can automatically on its own learn all these features, we concatenated this encoded layer with these additional features right before classification. And the performance of the model improved. This is some trick you can also follow in the works you do. But the idea here is that instead of relying on a big neural network to learn features, can you enhance the existing neural network by adding some extra features, which might be useful. This worked, fortunately. Our accuracy is improved. I wouldn't get too much into what those accuracies and everything was, but there's going to be a paper published soon where you can find everything. So this is not a new idea, by the way. There are several other papers talking about novel architectures which are specifically made for edge devices. Mobile nets, SqueezeNet, there's an MCU net as well. You could check these papers out and they'll tell you about new kinds of convolutional layers, new kind of residual networks, which are more hardware friendly, let's say. All right, that was our first bit, first technique, I should say, for Edge AI. Now, quantization. Let's go back to our VGGNet. So, TensorFlow uses 32-bit to represent numbers, the parameters, but what if we use 16-bit or 8-bit or 4-bit? And it's pretty obvious. If we use that, our memory footprint would be halved, and then a quarter, and then an eighth. So why don't we do it? Why do we use like 32-bit numbers, and why not, let's say, 4-bit representation? In fact, some people do use smaller bit representations. Even they have gone to the extent of binarizing the weights of neural networks. In some of the studies you'll see, these are called binary networks, by the way. They have binarized the weights, the activations, the outputs, even the inputs. And these binary networks are very light because now you can represent a weight by basically 1 bit, theoretically. And then there's another added advantage as well. So I told you about those MAC operations. When you binarize everything, those MAC operations turn into a simple XNOR gate operations. So when you're talking about actual hardware, what happens is people are designing specialized hardware for this as well. So you can just, your neural networks will be executed going through XNOR gates, no need of like your NAND or other gates. This is really low-level embedded systems kind of thing. So what happens when you do that? Of course, accuracy takes a hit, but how much hit does it take? And some research on it is very, very optimistic. And this is one of the papers which I came across. You can look at these 3 solid lines here. You see the red line, the blue, and the green one. So red line is of a convolutional neural network trained on CIFAR-10 dataset. And this is the validation accuracy of that convolutional neural network. Oops, sorry. And you can see it goes to around 10% after about, I'd say, by 150, 180 epochs. But look at the 2 binary nets there. Their error is a little more than your fully convolutional neural network with like floating point, 32-bit floating point weights. But if you train it more, as you go higher in the higher towards higher epochs like 3, 4, 500, you'll say that all of them are converging to about 10%. At the end of the day, your binary networks have only a little more error than your full-fledged 32-bit neural network. So, when we talk about neural networks, there's a competition that I have got 97% accuracy and I've got 97.2, so mine is better. But at times when you actually deploy this, do you need that 0.2% increase in accuracy, or you need half the cost of deploying it on a very cheap hardware? So these are the things, when you deploy neural networks, you come across these problems. And not just that, there are other reasons as well. For example, Google's tensor processing unit, released in 2016, it works only on 8-bit integers. And NVIDIA, some of the chips, some of the GPUs also are 8-bit as well. So no 32-bit numbers, only 8-bit numbers. One more thing is that floating point operations like multiplying decimal points 3.2 into 4.2, which we take something as granted, many of these edge devices do not have processors for floating point operations. They can only multiply integers. So there are kind of ways that you tackle that in hardware as well. And like quantization, again, is a part of that. And not just, so there are many different types of quantization. You can read a lot of papers, a lot of work is being done on it. We also did some, but the thing to think about is that you take a 32-bit number, 32-bit representation of around of 100 million parameters, and you compare it with like a 1-bit representation of those more than 100 million parameters. And somehow, after 400 epochs, the accuracy is almost the same. So what does it tell us about neural networks? What is more important in neural network? Is it about the actual magnitude of those weights and activations, or is it about the network structure itself? That's something to think about. Next on, we go to pruning, and this is the thing which I spent most time on the project on. And we also had a novel way to prune, which I'll talk about a bit. And okay, so I'll give you a basic idea of what pruning is. It's a very old idea, in fact. In neuroscience, it was already known in I think 1980s or 1990s, that if a part of your brain gets hurt, suppose you're traveling in Red Line Lewis and a teenager throws something at you, and it hits you in the head, and it hits the region of your brain which has learned how to program in Python, so you'll forget Python programming. But the good news is there are other parts of your brain which you can which can relearn how to program in Python. And this is where the pruning idea comes from. Can you actually chop these neurons off, or chop some of the connections between those neurons off, and still the other neurons would learn what their ancestors had learned and still do the same job? And to do somehow, that's why I'm talking about it. And one of the very early ways to prune neural networks was simply this. So if you plot a histogram of all your 100 million, 150 million weights, you will get like a good smooth distribution, I assume, and you set a threshold. You say, if the magnitude of my weight is certain much beyond this, around 0, it's a little bigger than 0, I'm going to keep it, otherwise I'm going to chop it off. So if you chop the ones close to 0 off and retrain the rest of your network, you get this kind of like a bimodal distribution, and accuracies suffer, as they do they suffer in quantization, but not that much. All right, there is something called unstructured and structured pruning as well. And it is quite important, that's why it's in the slide. But what it is and why it is important, that's what I'm going to explain you now. So you have a neural network, you can remove connections between some of the neurons, and you end up with a matrix like this. So the weights can be represented as a matrix, and you can get this like an unstructured sparse matrix if you want. Something like this, where some elements are non-zero, the blue ones, let's say, and the white ones are 0, right? But in structured pruning, what you do instead is you chop off whole of these neurons. So all the connections going from or coming into the neurons are chopped off. And it's when you get these structured matrices, and these structured matrices are where either the row is all zeros or the row has all numbers. These are structured. What is the benefit of this? So we're going back to our MAC operation now. So multiply and accumulate. So how is that MAC operation actually executed in the hardware? So this is your, let's say, your computer, your processing element, wherever the neural network is being executed on. Inside that thing, you'll first read the weights from the memory, and also you will read the activations of the inputs you want to multiply it with. Right? You read it into from the memory, then you go to your ALU, your arithmetic logic unit. That's the unit that performs the calculations, the actual multiplying and adding operation. And then you write that sum to the memory again. Now, an interesting finding from a few of the researchers at MIT was this. So let's suppose the energy that you take in performing that computation, like A into B is equals to C. Let's take that as unit 1, right? Compared to that, the energy that is consumed in actually fetching that weights from the memory is about 200 times more. So you're spending more energy, more time, more latency in fetching those weights and activations from the memory rather than actually performing the computation. And it is very important in edge devices, especially with batteries. You know, all these Apple phones with the bionic chips with neural processing engine, what do? They actually bring the memory as close to your processing element as possible, so that this latency and this higher consumption of energy is kind of minimized. There are other ways to do that as well, data flows. But this kind of an idea exists with some of you might know about cache memory in your computers, right? It's like a smaller memory, but it loads things faster. So it's a similar idea in edge devices as well. So the closer your memory is your ALU to your ALU, the lesser would be the energy consumed and the lesser would be the latency. How does it affect this one, structured or unstructured pruning? So when you have an unstructured sparse matrix, something like this, you still have to fetch from the memory all the positions where your weight has values, for sure, as usual, but all the positions where your weights have 0 values as well, which is basically amounting to the same thing in terms of reading from the memory, right? But in a structured pruning, what you can do is you can completely ignore that row which has all 0 elements. Simple idea, but highly effective. So if you don't look at these MAC operations, the advantages of unstructured and structured pruning are sort of similar, because let's say I pruned 50% of the neurons of the parameters in an unstructured way and 50% in a structured way. Like you can say that, okay, they have same number of parameters, so you can store them in the same memory, but that's not true. And that goes back to this. Well, so I told you about a novel pruning technique which we sort of made during this work at CEDA. And the inspiration of this is something called SciNet. I highly encourage all of you to read this paper. I'm from a physics background, so this is about how can you model physical processes using neural networks. So what they did, they again had a neural network, an encoder-decoder architecture like this. And what they fed it in was data from actual experiments of physics. So one of the examples we're going to take is a damped pendulum. So it's a pendulum and it has some damping constant here, so it's going to die down eventually. So they fed the input time series and expected the time series of the output from the encoder-decoder. By the way, this is a different encoder-decoder. You see there's a question neuron here as well, which is not in your usual autoencoder architecture. So this question neuron asks a question and then you get an answer at the end. Very I would say romantic way of naming the things, but yeah, it's highly very catchy to say the least. So if you model a damped pendulum from physics, from differential equations, you'll get this kind of equation. So x is the position, t is the time. So you get a double derivative of x multiplied by the mass. K is your spring constant here, or hard or soft your spring is. X is again the position, and B is the damping factor. It's like how damped the oscillations are. Usually what's done, you take that m on the right side of the equation, you multiply k by, or divide k by m and b by m, so you end up with 2 parameters that can be changed. So what they did is they trained this autoencoder, decoder, the SciNet, let's say, with 3 hidden neurons and with this network. And after training, you can see that the predicted and the true time evolution is on the graph. After training, they looked at the activations of the 3 hidden layers, 3 neurons in the hidden layers, and they found this out. Now I want you to look at them very carefully. So 2 of them are like surfaces, which have a certain slope, have a certain intercept and everything, right? And the third one of them is like 0, completely fat, no activation. It hasn't learned anything. And if you go back to the equation, there are only 2 variables that are controlling the oscillation of a pendulum. That is the spring constant and the damping factor. So what the neural network has actually learned is something physically very significant. The damping factor and the spring constant. And the third neuron, as there was nothing else to learn, didn't fire at all. So the idea to take from it, or the idea that at least I took from it, is that the latent representations in an autoencoder, let's say, do have physical meanings. And that's why when I showed you earlier that I chopped up the decoder from the autoencoder part and I still got the results, that idea comes from the same thing, that the encoder layer does have some physical meaning which you can then use later on. So we used this idea, and how we used it, I'll give you an example and give you some vague details about it. So this is VGG16, which I again showed you earlier, but now with a nice little diagram, and it was trained on CIFAR 10, right? So after training, let's say you have your validation set, or even if you have your training set, you send all the examples one by one through the network or in batches, and you record what the activations or the outputs of each of these layers were during that, after training, basically. An example is this. So I take the first fully connected layer. I think it has 3 fully connected layers, VG16 or 2, I think, yeah, 3. 3 fully connected layers. So I take the outputs of first fully connected layer and plot them here. So what I've done is I have separated these outputs by class. So for example, I have bundled the activations for samples which are of class 0 into this one box plot, and from class 1 into this box plot, right? Let's say this is the all training, this is all the training data. So essentially what we're trying to do is classification. What we're trying to do, we're trying to draw a line between these two data distributions to say, okay, something is above this or below this, it belongs to class 1, or below this class 0. If I was just doing like a binary classification between 0 and 1 classes, I could just draw a line here and say, if the activation is above, let's say around 0.1, it is class 1, and if it's below 0.1, it's class 0, right? Simple. So this is the ability of a neuron in a classification task to separate classes, right? And we came up with a way to quantify that. For example, you can see here that this neuron is good enough to differentiate between classes 0 and 1, but not so good to differentiate between classes 2 and 3. So they are almost the same, the activations for them. So it cannot do anything with this latent representations. So came up with a mechanism to score basically your neurons or your filters in terms of if you're using convolution layers. And we chop those off with the ones with the lowest score. We experimented with it on ImageNet, ResNets, CIFAR10, VGGNets, and yeah, the results are going to be out in a paper. I'm not going to bore you with that. But yes, what did it teach me about neural networks? Again, so this is like pruning and quantization has been like a resounding board about the architecture of neural networks in general. Is that now and ever again, what we are seeing is, if you have a prune network, let's say you have a fully trained network, you prune it and you retrain it and you get another network, right? What if you were to start training with that network? Would you have the same results as your original unpruned network? And the answer is sometimes you can actually have better results. So if you're having like 97% accuracy, you can get to 97.2 if you prune 10% of the layers. It's fascinating because if you think about it, we already knew about this, but we never thought about it. We all know about over-parameterization, and neural networks with their hundreds of millions of parameters are usually over-parameterized. And if you prune some of them, and you prune them smartly, you might get a little improvement in your accuracy. But again, that is for publications, might not be that useful. Again, so we did this work about a year back, and if you check now, if you just Google quantization and pruning, you'll find hundreds of papers on it. Just every Tom, Dick, and Harry gets a paper on it, including myself. And the good news is most of them are useful, like most of them are good, and very few of them are, you can say, oh, this is shy, this just made up some accuracy numbers in the paper. So where is the designing of neural networks heading? And I think one very strong trend is what you can see from pruning papers. Before, the pruning papers were something like this, that you have a trained network, you prune them, you have some sort of metric, and then you train them again, and then you get a new prune network. But now they are evolving the architecture of neural networks. So your neural architecture search is something you'll find most people are working at the moment. This is where you've given some sort of, many people use genetic engineering for it as well, but you give some sort of an architecture and the program automatically sort of learns that architecture, keeps on adding bits and pieces to that. So that is sort of where the research, let's say, on neural networks architecture development is at least heading. And that was all. And I will take questions now. Yes, oh, we have a question already, do we?
Hi, Inder. I have a question. How is pruning different from dropout layers?
Okay, so dropout layers is like while training, you don't actually, when training you drop out layers, drop out neurons within that layers randomly, right? But they're still there at the end of the training, right?
Well, they're there in testing, not in the training. So you drop them out during training.
Yeah, but the weights are still there, right? I mean, weights still have values, don't they?
No, there wouldn't be weights, I guess.
So dropout is random. I think.
It's random, yeah. But there wouldn't be weights assigned. Like they'd be dropped out during the training process, and then they'd be put back in testing in order to like get weights in case they actually have any to learn without the neighboring nodes or neighboring neurons rather. Sorry.
No, I don't think so. Dropout is you're actually dropping out those layers permanently.
The neurons.
Huh?
You're dropping out the neurons, right?
Yeah, the neurons. The neurons. You're not dropping them permanently. It's otherwise you'll be pruning them.
Yeah. So
dropout is another regularization mechanism, you can say.
Yeah.
But it's not pruning. You're still keeping those neurons.
So in the case of pruning, you would drop them out during training as well as testing.
No, after. So in this case, in the technique we develop, we chop them after training and then retrain them. But there are methods when they chop off neuron while training as well.
Okay, and then secondly, you had unstructured pruning and you had structured pruning. So I'm assuming that the structured case would be like not randomized. Or was it like, were neurons randomly dropped, and then like how was the structuring done in that case?
So it depends on the technique you're using. So when you drop a whole neuron or not just some connections, you will automatically get like a structured sparse matrix, because in the matrix of your layer, let's say you're removing one row or column depending on the way you represent it. So even if you drop neurons randomly, but you drop whole neurons, you will still end up with structured pruning. I'll explain later.
Yeah, sure, please.
Yes, there's one more question there. By the way, I didn't get a chance to show you the embedded code sort of aspects of this project, but like if some of you who do embedded coding in C, C++, we can talk after the talk as well. Yes.
Hey there, sorry, just a question on the. So suppose if you're working with a model that has billions of parameters, or with new models that have lots of parameters. So what's your experience using off-the-shelf tools like like Onyx runtime? If you've heard about that, these runtimes, they kind of offer you tools that just take models directly and do the pruning for you. For example, taking a 32-bit trained model and then putting it directly into like 8-bit values. So do you have experience in using such tools, or?
No, like I didn't get your question. I think the first part of the question is like, do you use off-the-shelf 32-bit trained networks and then?
No, sorry. So have you heard about Onyx runtime?
Yeah.
Yeah. So in your experience, if in cases where there is a model that has billions of parameters, then you don't know about the architecture and you don't want to dive into, say, what the model does.
Okay.
And then instead, if you're using ready-made runtimes to just kind of do the pruning,
okay,
then how does that compare? And is that what is your experience in that?
Well, so the Onyx thing is a representation of two neural networks. Firstly, it's like a standardized way to store neural networks so that all libraries can do it. And as of now, if I know, like especially things like TensorFlow and PyTorch, if you compile an Onyx model in one, it won't work in the other. So the support for it is not that well. But using off-the-shelf, again, the thing is like when you use off-the-shelf thingies, they're usually made for like big CPUs or GPU machines. When you are talking of edge devices, especially given that how many different kinds of edge devices you're using, I'm not talking about Raspberry Pi here, by the way. So depending on what kind of, again, like embedded programming platform using, you might have to do your own work. My project was again like very researchy. I still had to use all these different tools, had to do everything myself. But even in the industry, when I see people have to do it themselves, there is TensorFlow for sure, and I tried using that as well. But again, it has support only for, I think, few kinds of boards. And so you ultimately have to do some bit of things by yourself. Interesting point, that reminds me of another thing. So Adnan Ashraf, who was also on the project, he was doing his master's research back then. And so when we wrote the embedded code, we were using ARM's library for neural networks. So like there is PyTorch, there is CMSys by ARM for running neural networks on their embedded systems. So taking into account like how their processors are structured and stuff like that. So he wrote embedded code using their functions, like they are fully connected, their convolutional layers, and then he wrote his custom functions. And he found out that his custom functions consumed way less current than ARM's library. So that again boils down to this thing. So when you're working on projects and when deploying things, the amount of parameters you can play around with, the nitty-gritties you can do while deploying it, it's a lot. Again, if you're dealing with Raspberry Pi, yes, you don't have to do much, but then when you're getting into a product or productionizing something, yes, you will have to do all these things.
Thanks.